Keed. His topic is dependence of heating and active region coronal loops on the magnetic flux at their feet. So Sanjiv, you have 15 minutes for your talk. I'll give you a warning after 12, and then we'll still have a few minutes for questions at the end. So take it away.
Thanks, Todd. Thanks to SOC for giving me this opportunity. When we compare solar X-ray corona with the surface magnetic field, we can see there is one-to-one correlation in the intensity enhancement in the corona and magnetic flux enhancement on the surface of the sun. The stronger magnetic field active regions are brighter. That further suggests that stronger the magnetic field in general on the surface of the sun, the brighter the solar corona is. Solar AIA 94 image more or less shows similar behavior to XRT image I showed in the previous slide. Again, the active region with the strongest magnetic flux is brightest. So there is one-to-one relationship. Consistently, Tiwari et al. Showed that the stronger the magnetic field in the loop, brighter the loop will be. Heating rate is inversely proportional to length of the loop, and the volume of the loop is also well known. Now, in the past, it has been found that sunspots are dark, not only on the surface, but also in the X-ray corona. None of the bright loops originate in sunspot umbra, but it has also been reported that the loops, at least some of the loops rooted in sunspot umbra, are the brightest ones among others. The brightest loops are associated with flux tubes leading to the umbra of sunspots. This is an example from AIA. This is a very bright loop that originates from sunspot umbra. Falcone et al. And Moore et al. Found that brightest loops are rooted near neutral lines, and they proposed that flux cancellation at the feet of the loop might be inducing coronal brightness. So there are some obvious questions here. Why sunspots, particularly umbra, are usually dim in coronal UV and X-ray images? You can always suggest that it is because of the suppressed convection in sunspot umbra. But then what is happening with what is special about some loops that stem from an umbra, but are the active region's brightest coronal loops in UV and X-ray corona at a given time? Are the brightest active region coronal loops always rooted at neutral lines? Does a loop's routing pattern, magnetic setting on the photosphere, tell us something about its coronal brightness? To address these questions, we selected a couple of active regions from SDO, HMI, and AIA. We followed them for more than 24 hours. These active regions have fully developed sunspots in each magnetic polarity. They are close to disk center and they're non-flaring. These contours strictly outline umbra penumbra boundary. So they are outlining outer umbral boundary. Before I go to show you coronal loops, it is important to understand where in sunspot, in high resolution data, we can see where in sunspot a loop is rooted, if it is. So a loop that is rooted in sunspot will be rooted either in sunspot umbra or in spine fields of penumbra. These red pixels are spine fields which are outward extension of umbral field, or in and the penumbra is formed of spine fields and penumbral filaments. Penumbral filaments are stretched, magnetized, convective cells. So what is important here is, if a loop is rooted in sunspot umbra, then it is in a non-convective environment. Convection is strongly suppressed here. Whereas if a loop is rooted in spine field, let us say anywhere in penumbra, that will be spine field. Those are the field lines which can reach to corona, because these penumbral filaments are convective cells. They are down to the surface. So if a loop is rooted in sunspot penumbra, that means it has a convective neighborhood. All these numerous penumbral filaments are convective in nature. Okay, now we followed this active region for, this is one example of active region for 25 hours at 3-minute cadence. And in particular, in 94 image, In the movie, you can see there are many bright loops. There are also intermediate bright loops. I will show you some examples on the movie frame. What we noticed in the movie of two active regions following for more than 24 hours each at 3-minute cadence, that bright loops are episodic. There are repeated subflares in sets of loops with a given routing pattern. The brightest loops are rooted in umbra at one of their feet, with their other feet in opposite polarity unipolar plage or mixed polarity plage or penumbra. And they never end in opposite polarity umbra. We don't see any loop that connects sunspot umbra to sunspot umbra in any of the EUV channels. The plage to plage loops have only intermediate brightness. AIA 94 images are dim in umbra. Now, this is an example of brightest loop. This one connects sunspot penumbra to sunspot penumbra. We also verified that the brightest loop in 94 images are actually hottest. And here is another intermediate bright loop. You can see this has intermediate temperature, and there is this fan loops which are dim, and you can see temperature is low there. This is another set of example where penumbra connects to a mixed polarity region here. And this is among the brightest loops as well. Another connection here, this particular loop, if you see here in the movie, this is connected to here in sunspot umbra at 1 foot, and other foot point is in a unipolar plage region here. This example is from the second active region, where there are two bright loops here, and one is connecting sunspot umbra to a unipolar plage region here. The second one is connecting sunspot umbra to a mixed polarity plage here. Then there are many intermediate loops, intermediate hot loops, which are never as bright as the connections I showed you before. So this one connects, this example, this connects plage region to plage region, and they never become as bright as the other brightest loop. Now, the question is why we don't see any umbra to umbra loop, whether umbra to umbra loop exists at all. To find out that, we perform nonlinear force-free field modeling. And these active regions are very suitable actually for this because they are almost flux balanced and they are at disk center. So first we compare the AIA 94 loops with the field lines, model field lines. Once we were confident that they match well enough, we tried to trace the umbra to umbra connections. And we found there are many loops that connect sunspot umbra to sunspot umbra. Either they are short or long, and none of these match with any of the observed loops, not only in AIA 94, but in any of the AIA channels. When you combine these observations, this is a sketch V2. So let's start with the brightest loops. Brightest loops of an active region are rooted at one end in sunspot umbra or penumbra, and at where you have a strong magnetic field, of course, and at the other end in unipolar plage where convective freedom is there, convection is possible, or in penumbra which has convective environment, or in a mixed polarity region where again convection is possible, but here magnetic flux cancellation could drive additional heat. The loop that connects plage to plage, they are only intermediate bright because although they have freedom of convection at both foot points, the magnetic field is weak in this loop than as compared to these loops. So this never becomes as bright as these loops. That means freedom of convection and magnetic field strength together determines the heating in a loop. Now let us see umbra to umbra loops. These loops are frozen in sunspot umbra due to strongly suppressed convection. Therefore, even if they have strongest magnetic field, they are never visible, whatever their height is. Now you can always ask what is happening here. This is because of the long length of this loop. This has same connectivity as this penumbra to penumbra, but this is very long, so it is dim. These are fan loops. So one important point here is if you look only at 1 foot point of a loop, you can never tell whether it will be during the evolution of the active region, whether it will be hot or dim, or anytime it will be intermediate bright and so on. But if you look at the other foot point, you can tell whether this loop will ever be bright or not. For example, this one, if it is connected to a plage, unipolar or mixed polarity or penumbra, there is a chance that during the evolution, this will become among the brightest loop. Whereas if the loop is connected to a sunspot umbra, it will not become even visible in EUV. Sometimes you can see dim loops, but every time you see a dim loop that connects sunspot umbra to umbra, there is a light bridge, which is are sometimes large umbral dots, and these are sign of convections in the umbra. Now, if you revisit this plot, the stronger the magnetic field, brighter the solar corona is, and somehow can measure the density and emission from this loop, that will show a negative correlation. You have a stronger magnetic field and you have dimmest loop. That means this plot is perfectly correct for the loops when you consider only bright, dim, and brightest kind of hotter loops. But this cannot be fundamentally correct to think that stronger the magnetic field, brighter the solar corona is. Convection plays an important role, and together these determine the amount of heating in a loop. This is what I just said, so I will skip and go to this slide. Recently, this third connectivity, where you have possibility of magnetic flux cancellation, has got a lot of stress, and magnetic flux cancellation seems to be a dominant mechanism out of these three for an active region brightness. We have found in the past that flux cancellation transiently made bright loops, and there was interaction between these erupting loops with the overlying braided structures, and many subflares were formed. A flux cancellation rate of 10^15 Maxwell per second was observed. Jitta et al. Found loop in hot loops in AIA 94 are rooted at magnetic flux cancellation site. In active region, the core of active region, we found many tiny dots, which could be small loops. Loops and surges also show magnetic flux cancellation. And everywhere in these papers, we found cancellation of the order of 10^15 to 16 Maxwell per second. Priest et al. Gave cancellation.
You have about 3 minutes left.
Okay, so I will skip this slide. I will come to this part of my talk. The question is, because there have been a lot of stress on cancellation heating, question is, are the brightest coronal loops always rooted in mixed polarity magnetic flux? This is what we recently addressed. We followed an active region for, again, more than 24 hours. We calculated hot emission, hot 94 emission, following Warren et al. Method by removing warm components, and plotted histograms of the foot points of the loop. And histogram, the foot point of the loop were selected based on the non-force-free modeling. We found that about 40% of the loops, hottest loops, they are rooted in unipolar magnetic flux. So this doesn't support cancellation idea, but 60% of loops were rooted at least at one foot point in mixed polarity magnetic flux. This strongly supports cancellation idea. And there are more papers finding better. For example, Jitta found 70% of the loops were rooted in mixed polarity magnetic flux. We also found that the loops with both feet unipolar are 15% shorter lived on average than the loops having mixed polarity magnetic flux, but their peak intensities are equal. Before I go to my conclusion slide, I have listed some points that support cancellation idea and some points that challenge cancellation idea. Majority of coronal loops show mixed polarity magnetic flux, at least at one of their feet. This supports cancellation idea. The hottest loops are often episodic. Anywhere you have visible flux cancellation on the surface, they're often accompanied by transient coronal heating. In Evlan et al., we found that unipolar plumes have additional heating whenever there was presence of mixed polarity magnetic flux on the surface. That means there is additional heating driven by cancellation. Different sizes of jets are triggered by magnetic flux cancellation. Recently, jet-like structure is seen at the base of some coronal loops also. different fine scale explosive events are seated at mixed polarity magnetic flux. In most of the small loops, heating propagates from one end to the other that strongly supports cancellation idea. Now challenges. We found that there is absence of mixed polarity magnetic flux. There are about 40% of brightest loops are rooted at unipolar magnetic flux in both our foot points. As I said before, magnetoconvection and field sprint at both loop feet possibly drive much of the heating in those cases, even if there is mixed polarity magnetic flux that can do that. Cancellation could probably provide additional heating as seen for plumes, but whether cancellation is fundamental for heating loop is far from established. If flux cancellation takes place at one end of the loop, one should expect asymmetric heating extending from the cancellation side to the other end. This is not commonly observed. For tiny loops, probably it is easier to imagine and consider, but for typical loops where heating is often symmetric and starts from the apex, similar to flares, it is difficult to find out cancellation playing an important role. If reconnection happens, this is another thing, and then if cancellation is the main driver for the loop heating, one would expect each coronal loop to appear as a jet, something like this. Finally, wave heating doesn't require cancellation. In conclusion, there is a systematic dependence of the heating in active region coronal loops on the photospheric magnetic flux at their feet, freedom of convection, and strength of the field together at both of the loop points determine the amount of heating in a loop. Magnetic flux cancellation, which is often accompanied by emergence, seems to play an important role in heating loops and driving fine-scale explosive events, but challenges endure. Our observations provide new insights and constraints to future 3D MSD models of active regions. Thanks for your attention.
Thank you, Sushant. Very nice talk. Very interesting result. We do have a couple questions. I'll go to Hugh Hudson's first, which is loop brightness as it relates to magnetism is often parameterized as B to the alpha times L to the beta, or some such relationship. Would you agree that this seems kind of misguided given the strong relationship to the foot point properties? And I think we know your answer, but I'll let you comment.
I cannot see the, well, I cannot see the comment. Maybe, can you, sorry, can you go ahead, read again for me?
Sure. Loop brightness is often parameterized as the magnetic field and the relationship between the magnetic field and the length of the loop, or something like that, to some power or other. Does that seem kind of misguided given what you found, that it has to do more with the foot point interactions, or do you think there's some value in that?
I think it is, yes. Well, you can see there is a clear dependence of heating in coronal loops. Of course, length is important, as I showed you in the previous slide, but there is a systematic dependence on the heat on their foot points, magnetic flux on the foot points. We find a strong evidence for that.
Okay, we have another question from Katie Lecca, which is, has the lack of mixed polarity flux in the 40% of the brightest loops been confirmed with higher resolution observations, or is this something that we would need DKIST or something else for?
Yes, definitely. That is actually, I'm also looking for SOT SP magnetograms if we can find more loops of that. So definitely the 40% is at the detection limit of HMI. So we also need future super HMI kind of instruments.
Yeah, who wouldn't love that? One last question is, how confident are you that you can actually identify the foot points of the loops with the locations in the photosphere? In other words, I guess, at what height do the loops appear, and how confident are you that you can actually trace where the foot point is coming from when differentiating umbra and penumbra?
Yeah, that is why we took help of extrapolations to exactly track the foot point in the photosphere.
Okay.
And once we are very confident, extrapolations match with the observations in other loops, only then we go for comparing the loops we are interested in. Okay,
great. Thank you. Well, if you could stop sharing, and then we'll move on to our next talk. Thank you again very much for that very nice summary of your work. It's very appreciated.